Okay, so here's where we're going to try and find the instantaneous rate of change using the formula, but without a table. Okay, we're going to try and use some algebra here to try and solve this. So let's try it for the function f of x equals x squared and determine the instantaneous rate of change at x equal to 1, so without a table. So first of all, we're going to look at the formula. Okay, the average rate of change equals f of x plus h minus f of x all over h. Okay, we're not going to define a value for h yet, so we're going to just leave h floating and try to simplify this algebraically. Okay, so if we do this, we're going to plug in 1 plus h goes in for x, okay, in this formula, and then 1 goes in for x. And once we've done that, we've got 1 plus h squared, because it's x squared, minus 1 squared all over h. We expand this, we get 1 plus 2h plus h squared. That's perfect squared, that's how it expands. And then minus 1. Those 1's cancel out. 1 minus 1 cancels out. And we end up with this expression, which we notice now that h is a common factor on the top and the bottom. Now, we have to remember that still, we can't just cancel this out because h can't equal 0. So if we cancel that out, and we want them to be equivalent, we have to write that h cannot equal 0. Because in this case, h can't equal 0. But if we didn't write that here, then 2 plus h, well, you can evaluate that at h equal to 0. That you can't, so they would not be equivalent in that case. So you have to write here h cannot equal 0. Okay? From this, well, you can now see that this one is pretty easy to predict. If you plug in values of h getting closer and closer to 0, so that the secants, okay, so if you look at this and you've got f of x equals x squared at x equal to 1, okay, there's the tangent, okay, as h gets close to 0, so there's 1 plus h, say, go up, and we've got a point there, and we got a secant. As h gets close to 0, these secants get closer and closer to the tangent. So as h gets close to 0, we can see the pattern here. It must be approaching 2. Okay, so if this works nicely like this algebraically, we can make really nice predictions that that is the instantaneous rate of change is 2 for that one. Okay, so mathematicians now thought that maybe this will work out nicely for a whole bunch of them. So they created this operator that you can apply to functions or algebraic expressions. It's called the limit operator, where you don't actually sub in a number for it. You make predictions of what's going to happen as a number, as a variable in that expression approaches something. So if we look at this, we could actually say that as h approaches 0 in this expression, this has a limit. No matter what value, if it's positive or negative, as h approaches 0, it keeps getting closer and closer to 2. So you could say that the limit is 2. It won't go past it if h is approaching 0. Okay, so mathematicians decide to use this operator on this expression for average rate of change in order to define the instantaneous rate of change. Okay, so the instantaneous rate of change is now defined as, so at some value x, as the limit as h approaches 0. So that means the limit as h approaches 0. Doesn't mean as at h equal to 0, as h approaches 0, is this of this arc. Okay, so the limit as h approaches 0 of this average rate of change is now going to equal the instantaneous rate of change, and we can say it's a limit, and now it's exactly equal. Okay, as long as we can get a nice algebraic expression for that. So let's try this out. Let's look at this nice quadratic function here. F of x equal to 2x squared minus x plus 1 at x equal to 3. Well, here's our expression for instantaneous rate of change now. We're adding the limit to our old arc expression. Okay, so f of 3 plus h, because x is 3, minus f of 3 all over h. Let's see what happens when we simplify this. Okay, so we're going to plug that in, still writing the limit there. So 2 times 3 plus h squared, because that's what goes in there, minus 3 plus h plus 1 minus the function at 3. 2 times 3 squared minus 3 plus 1 all over h. Okay. And once we've simplified, expanded and simplified that, we get this. Now I get a little bit lazy at this point. We can't stop writing the limit as h goes to 0, but we can write in these little diddle marks. Okay, so that means that it's still there. Okay, so 2 times that expanded gives us that. Okay, and you simplify that, you're going to get this expression. Again, there's an h on the top that can be canceled out with an h on the bottom. But because we're writing this as limit as h approaches 0, it's assumed that h doesn't equal 0. So we're going to not have to write in that h doesn't have to equal 0. It's assumed it by this operator now. The limit as h approaches 0. Not as h equals 0, as h approaches 0. Okay? And from this, you can imagine, so we're doing a limit intuitively now. There is more to the limit than what I'm describing, and we'll look at that later. But we're using this as what its possible limit could be. As h approaches 0, the value of this expression keeps getting closer and closer to 11, because this becomes negligible. And the limit is 11. Okay? So you can kind of think of this as, so we can write the limit for that one is 11. If you think of a function that you know, like 1 over x, just look at the right side of it. Okay? As x approaches infinity, this function never ever touches the x-axis. Okay? It never touches the x-axis. It never goes past it though. So its limit, because it can get as close as you want, and then closer, and then even closer, without actually touching, there is a limit. It can't go past, but it never reaches. So the limit as x goes to infinity for something like 1 over x would equal 0. Even though the function itself will never equal 0, the limit does equal 0. Okay? So it's because it's the limit of what this would be as x approaches infinity. Okay? So that's a little idea of what the limit is. Now, let's try another one here. F of x equal to 1 over x at x equal to negative 2. Again, we're going to use this formula. Okay, so for the instantaneous rate of change, so f of negative 2 plus h, so we're going to plug in negative 2 plus h in for x, and then negative 2 in for x. Okay, when we do that, we get this. Now we've got a bit of a problem. This isn't as nice as the polynomial. So what we do here, the little trick that we apply when we have a rational function, is we have to get a common denominator. Okay, so getting a common denominator looks like this. So you have to multiply the left denominator by negative 2, the right denominator by negative 2 plus h, and whatever you do to the bottom, you must do to the top. So this is how you go about getting a common denominator. Now you bring them together. When you bring them together, you get this. Okay, the top actually simplifies to negative h. Negative 2 minus negative 2 plus h is going to give you negative h. The denominator stays the same, and then you're dividing the whole thing by h. So the h on the top cancels with the h on the bottom. Once you've done that, you've got the limit as h goes to 0 of negative 1 on the top over negative 2 times this. I didn't simplify that because it's not necessary at this point. Okay, so as h approaches 0 on this thing, it is pretty clear that negative 2 plus h on the bottom approaches negative 2. Okay, h isn't in these two pieces, so we're really just looking at this. So as h approaches 0, I'm pretty certain that this piece approaches negative 2. So we can now remove the limit because we've applied that operator on this expression, and we get this, which is equal to negative 1/4. And that would be the slope of the tangent of 1 over x, the function 1 over x, at x equal to negative 2. Okay? We can draw the graph of that to see if that makes sense. So 1 over x on this side at x equal to negative 2, the slope is negative 1/4. That makes sense. Okay, so that makes sense there for that, that graph. That might be negative 1/4.